Okay, here's a little introduction to integration. Up here I've written a couple of formulas. The indefinite integral of f of x dx is equal to big F of x plus c, where big F of x happens to be the antiderivative of little f of x. That is, if I take this big F of x and I differentiate it, I get little f of x. And then over here I have the definite integral from a to b of f of x dx, and that turns out to be big F of b minus big F of a, again, where the derivative of big F is little f. So this turns out to just be a number. This right here is a function. So this is an indefinite integral, this is a definite integral, and they have really actually two different definitions, even though the notation is the same. What they have in common is that whatever we get over here for this function, its derivative has to be the function that we started with over here. So now, what about integration? Well, we only have a couple of formulas to start with. The integral of x to the n dx is going to be x to the n plus 1 over n plus 1 plus c. Because if I take this and differentiate it, I end up with x to the nth. So I put the c on here so that I get all functions that are the antiderivative of this thing right here. So let's see how this works in real life. The indefinite integral of x to the third dx, well, that just says write down all the antiderivatives of this function x to the third. So that's going to be x to the fourth over 4 plus c. So there is the indefinite integral of x to the third dx. And what you want to notice is that this x and this x have to match exactly for us to use this formula right here. Okay, what about the definite integral from 0 to 3 of x to the third dx? Well, very similar. I'll just go over here and find the antiderivative, x to the fourth over 4, and then I use this notation to say that I want to evaluate it at 3, and then subtract from that what I get when I evaluate it at 0. So that's going to be 3 to the fourth divided by 4 minus 0 to the fourth divided by 4. Okay, and 3 to the fourth is going to be 81 divided by 4. This is going to be 0, so I end up with 81 over 4. So you can see in actual practice when I do this, when I have a definite integral, I end up with just a number. When I have an indefinite integral like this, I end up with a function, or a group of functions, a family of functions like this. All right, let's take a look at a couple more problems. All right, here I have another definite integral, the integral from 0 to 4 of square root x dx. Well, I don't have a formula for square roots, but I can take that square root and rewrite it with an exponent. So I'm going to change this then to the integral from 0 to 4 of x to the 1/2 dx. Now I'm okay to use my formula because I have x to some power dx. So I can just integrate here and get x to the 1/2 plus 1, which is 3/2, divided by 3/2. Well, if I divide by 3/2, that's the same as multiplying by 2/3. So I'll write this as 2/3, and then I want to go from 0 to 4. Okay, so x to the 3/2 divided by 3/2, that's the same as multiplying by 2/3. That's where that 2 comes from and that 3. All right, so now I need to evaluate at 4. So I have 2 times 4 to the 3/2, all divided by 3, minus 2 times 0 to the 3/2, all divided by 3. Okay, 4 to the 3/2, well, let's see, I'm going to take the square root of 4, that's 2, I'll cube it, that's 8, times 2 is 16, divided by 3, minus, well, this is just going to be 0, because 0 to the 3/2 is 0, times 2 is 0, divided by 3 is 0, so there's my answer, 16/3. Okay, not too bad. So I have a square root right here. I just write it with an exponent. Now I see that this x and this x match exactly, so I can use my formula for the antiderivative of x to the nth dx. Okay, what about this? We don't have a formula so far for the integral of sine t, but I can just use my imagination. I know that the derivative of sine is cosine, and the derivative of cosine is negative sine. So if I say that this is equal to negative cosine t from pi over 4 to pi over 3. How does that work? Well, if I differentiate negative cosine, I get negative negative sine, which is positive sine. So sure enough, that is the antiderivative of sine t, negative cosine t. So that's the thing about finding these integrals. You never need to make a mistake because you can always take that function that you get, differentiate it, and see if you get what you started with. Okay, so now I want to do this. So this is negative cosine of pi over 3 minus negative cosine, so plus cosine pi over 4. I have to write it like that. So cosine pi over 3, let's see, pi over 3 is 60 degrees, cosine is 60, 1/2. So negative 1/2 plus cosine pi over 4 is 45 degrees, cosine 45 degrees, square root 2 over 2. And let's see, I guess I could write this a little simpler as, how about square root 2 minus 1, all divided by 2. And let's see, did I go off the screen? No, almost. So square root 2 minus 1, all divided by 2 for that. All right, here we have a little true-false question. Is the integral of x cosine x dx equal to x sine x plus cosine x plus c? Well, intuitively, we don't know the answer to that question, but we can differentiate to find out for sure whether this is true or false. Let's let f of x be equal to this function right here, x sine x plus cosine x plus c. Okay, there's my big function, and what the question is this function the antiderivative of this function right here? That is, if I differentiate this, do I get this? Well, let's find out. So f prime of x is going to be, okay, what do I have? The product rule, all right? So the first x times the derivative of the second, cosine x, plus the second, sine x, times the derivative of the first, 1, plus the derivative of cosine x, which is negative sine x. So let me just write minus sine x right there. Plus the derivative of c. C is a constant, so its derivative is 0. I don't have to add anything on right there. So what do I have? X cosine x plus sine x minus sine x. Well, sine x plus negative sine x is 0, so this turns out to be x cosine x. So sure enough, there's that original function I had, and this is its antiderivative. So the answer to this is yes, that's true. That's a true statement. Let's look at another problem. All right, here I have another formula, another integration formula. The integral of e to the x dx is e to the x plus c. Remember, when we did derivatives, the derivative of e to the x is just e to the x. So it's its own derivative and it's its own antiderivative. Okay, so what happens if we come across something like this, a little more complicated? I notice that this does not match this, so I can't just use some formula that I have. So what I'm going to have to do is see if I can use my sort of properties of integration, which tell me that the integral of a sum or difference is the sum or difference of the integrals, and that constants out in front of functions, they can cross the integral sign. So let's see what we can do with this. I'll rewrite this as 2 times the integral of x dx minus the integral of e to the x dx. So what I'm doing right here is just using the properties of integrals that tell me that a constant out in front of a function like this, a coefficient, can cross the integral symbol, and that the integral of a sum or difference is the sum or difference of the integrals. Now I want to make sure that I put my dx down there every time. Notice that that's x dx and that's e to the x dx, so I can use this formula and my previous formula. So I have 2 times, okay, the antiderivative of x dx, x squared over 2, minus over here the antiderivative of e to the x, e to the x. And then you have to remember to put the plus c. In my classes, when we do this, we have an indefinite integral. Forget to put down the plus c, minus 2 points. So in any case here, those 2's divide out, and I get x squared minus e to the x plus c for the indefinite integral of this thing right here. So that's a little introductory look at integrals, some of the simple integral formulas, and just kind of getting used to the relationship between indefinite integrals and definite integrals.